Hi everyone, this is the optional content of ECE443. Today we are going to simulate indium gallium nitride-based cubic LED simulation. The most important part of this bonus content is that you will learn how to build your own material macro and perform the simulation using your customized material. Okay. And here I will just briefly talk about the background. So as you know, there are a lot of challenges in 3-nitride photonics like green gap and efficiency droop. So the green gap means that the power conversion efficiency decrease as your wavelength goes from blue to green or goes from red to green region. So you can see that the top figure, this PC LED warm white, this is phosphor converted light emitting diodes, and here is phosphor converted light emitting diodes, and CM is color mixed light emitting diodes. So with color mixed light emitting diodes, you have blue light, the combination of blue RGB lights and in combined and produce white light. The reason why phosphor converted light emitting diode has a higher efficiency compared to color mixed LED is because the efficiency of green LED is much lower compared to green and the red LEDs. Yeah, however, in theory, color mixed LED should have a higher efficiency compared to phosphor converted light emitting diodes. You can see in the bottom figure that the power conversion efficiency of blue and red LEDs are several times or twice larger than that of green LED or even amber LED. So this phenomenon is called green gap, and this green gap issue originates from the polarization of wurtzite 3-nitride material. So on the right hand side, I'm going to talk just a little bit about the efficiency droop. So the efficiency droop basically states that your efficiency decrease as your current density increase. And the reason behind it is also attributed to the existence of the polarization. So what is polarization then? So this is the crystal structure of wurtzite 3-nitrides. In an unstranded gallium nitride, you have a nitrogen atom surrounded by this. You have gallium atom, which is this white ball, and bonded with neighboring nitrogen atoms, forming this tetrahedral structure. However, because of the difference between electron negativity between gallium atom and the nitrogen atom, you form the dipole along these 4 bonds. And because it's not this structure, wurtzite structure is not central symmetric. So on the horizontal plane, this dipole cancel out with each other. And in the vertical direction, you have residual dipole moment propagates in the z direction, and this propagating dipole moment is known as spontaneous polarization. So under compressively stranded conditions, where your bond length in the horizontal and the vertical direction changes, you are going to introduce an perturbation to the polarization, and this perturbation is known as piezoelectric polarization, and it's caused by stress, external stress, or lattice mismatch conditions. And the total polarization is the sum of these 2 components, and the polarization should charge exists if you have a gradient in the polarization, and this will cause polarization induce the electric field and causing electron hole separation inside the quantum well. So to eliminate these things, we are going to simulate cubic GaN LEDs because cubicGAN, because it's cubic, so it has central symmetric properties. So those polarization will cancel out with each other, so you don't have polarization in your system. Okay. But cubicGAN or cubic indium gallium nitride, they are not defined. Their material parameters are not well defined in the software. So you need to customize your own material by putting in the material parameters. So the first step is to generate a macro file for cubic indium gallium nitride and the cubic aluminum gallium nitride. You can find the material parameters from external resources, such as the first one I list here. You have like a band gap or deformation potential parameters reported in this reference. You have band offsets of cubic InGaN and the cubic aluminum gallium nitride reported in this reference. You have donor and the acceptor activation energies of cubic system reported in the last reference. And you need to generate a macro file. You can name the file name by yourself. Here I use like my.mac located in your project folder. So what is inside this my Mac file is first you need to define your you need to label your new material. Here I declare the name of my material to be like C InGaN light LIB, and import basic name equals to C cubic InGaN. So this line declare the function of your material in the bulk structure. And then in the next line, you said you want to import a complex, and the name is different from the previous one. Here we have like a complex version of cubic InGaN. The reason we are adding a complex here is because then if it's in the quantum well or quantum structure, they are going to override the materials with this complex defined under this complex block. Okay. And you can declare the variables. X is for basic function, XW is for complex function. Okay, where you're going to use these two variables later when you define your material properties. Yeah, you can check that in the next slide. Then you just need to copy paste and make another version for aluminum gallium nitride. So you can see in the bottom, I put a comment here. The material properties defined with a complex argument works in active regions, such as quantum well, quantum wire, and quantum dot. More band-related parameters used in the K.P theory are defined in the function with the complex arguments. Yeah. So if there are any like materials redefined in the complex function, such as band gap and band offset, the values will override the predefined value in the basic function. So you know that later we are going to define the material parameters for this basic function and the complex function. So we have totally 4 blocks of data or 4 blocks of material parameters that we are going to define. Okay. Now let's take a look at one of the example in cubic InGaN. On the left-hand side is the basic one. On the right-hand side is the complex one. So if you remember, we have C InGaN and the CX complex C InGaN. So on the left-hand side, I have begin macro, a C InGaN. So this name has to be the same as the one showing here. And on the right-hand side, we have begin active layer and complex C InGaN. So this name also has to be the same as the predefined complex material library here. Okay. On the left-hand side, we set our material type to be semiconductor. band value 1, and we apply just a default electron velocity model and the hole velocity model. You can change it based on your own preference, but here I recommend you use the default one, which is used in gallium arsenide system. Okay, and then you can see that I can define the dielectric constant and put a variation. I said this dielectric constant is a function, and this function depends on two variables. One variable is x, and the other variable is temperature. But here I ignore this variable. I only consider the x term. Yeah. Okay, so then you define your relationship. It's just a linear interpolation from 9.7 to 15.3 because 9.7 is the dielectric constant of gallium nitride, cubic gallium nitride, and 15.3 is the dielectric constant of cubic indium nitride. So this x is the x you defined here. Okay. You have electron mass, you can define it similarly, and there are a lot of materials that you can define, and I already like attached a simple material file, macro material file with this PDF slides, and you can modify the material parameters based on the material you want to simulate. Similarly, on the right-hand side, you have the macro that works in active regions. Here, I said the layer type is strand complex, meaning that we consider the strand effect in the active region. We have gamma valley gamma equals to 1, valley L equals to 4. We have valley heavy hole valley and the light hole valley equals to 1. You can assume their default value, because if our heavy hole state and the light hole states are at gamma valley, so you have just single valley here. And we assume band offset of conduction band to the band gap of 0.675. You can choose a number that has been previously reported. If you want to learn more about how they implement the band offset model, you need to look up their manual. And then here, EG0 well, this is just an example. This shows the band gap at 0 Kelvin inside the quantum well. And this is defined as a function because your variation is equal to function, and this function depends on two variables. First one is the mole fraction. You see that this is XW. XW is different from the X defined on the left-hand side because we have XW defined for complex variable symbol. So you are going to use XW in this case. And we also have temperature but we are not considering any temperature effects in this block. So first you can define a band gap of gallium nitride at 0K, which is 3.31 electron volts. I can also define the band gap of indium nitride to be 0.56. And I set my Boeing parameter to be like 1.164 electron volts. And I just applied a simple Vegas law, considering non-zero Boeing parameters to calculate this band offset, band gap. Okay, this is just one example for cubic indium gallium nitride. You define the material parameters in the bulk structure and in the quantum well structures. And you can follow the same path to define the material parameters in the bulk and the quantum well for cubic aluminum gallium nitride. And most of the syntaxes are the same and explained in the CrossLight manual. So students who want to define their own materials that have the same like cubic crystal face can directly modify the simple file provided by us. But however, the Hamiltonian of hexagonal phase crystals is different from that of cubic phase crystal. So the band related parameters used are different as well. So you are suggested to create a new macro based on the one provided by CrossLight. For example, you need to copy the function like begin library InGaN or begin macro InGaN. These functions into your macro file if your material is quartzite or in hexagonal phase. Okay. And students who are interested in those parameters are expected to learn the physical meaning of each parameters by themselves. For example, like what is deformation potentials in conduction band and what is the deformation potentials in the valence band. Yeah, and what is strain and how the strain is calculated. Those information I would suggest you to look up from the literature or textbooks. Okay, so this is just a simple device structure. It's a single quantum well indium gallium nitride with 5 nanometer quantum well thickness and sandwiched by 10 nanometer intrinsic gallium nitride. And then we'll have a N-type gallium nitride with a doping concentration of 10 to 18. You have an electron blocking layer on the right hand side with a really high doping concentration of 5 times 10 to the 19. EBL thickness of 15 nanometer. And then you have PGAN on the right hand side. So generating this kind of layer file is maybe you are already familiar with the process, but the only thing you need to notice that is that here in the material library, you are going to put C InGaN lib. So this name has to be the same as the one you defined here, this one. So you are going to use this name and the program will decide if they are going to use the material parameters defined in this block or this block, depending on if you specify this region to be complex or quantum well, model equals to quantum well, then this block, the material parameters defined in this block will be used. Okay. So you can see that I define my first layer, C InGaN library, column number 1, variable symbol equals to X. Because this layer is gallium nitride, so I put my X equals to 0, and I assign doping concentration and the layer thickness. Okay. In the second layer, similarly, I put my X equal to 0 because it's intrinsic gallium nitride. In the third layer, I have a indium gallium nitride, and my model is quantum well, and my variable X is equal to 0.3. Oh, I should be 0.2 here. Yeah, so you need to change it to 0.2. Oh, maybe the typo is here. You need to use 0.3 for this device structure. And similar for cubic aluminum gallium nitride, you assign this label defined earlier in the material file here. And yeah, just need to repeat the same procedure for the rest of the layers. Okay, and in the solution file, basically everything is the same except that you need to specify this second line. Use macro file, macro 1 equals to like mine.mac. So here you tell the program to locate the material macro you defined by yourself. So with these lines, then everything will work as intended there's no difference between this simulation and the previous LED aluminum gallium arsenide LED simulation. Yeah, this is the only difference. Just need to add one line of code in the solution file, then you can use your customized materials. Now, for the rest of the parts, I think I already explained what those means in the previous lectures. So you just need to follow the similar steps. You change some of the parameters, and you can get your own results. So here, I think I also covered this before, because we switch the bias voltage at N contact. So it has to go from 0 to -10, meaning that meaning forward bias, with the initial voltage of 0.1 volts, a minimum step of 0.01 volts, and a maximum step of 0.1. But the voltage sweep stops when the current density goes above 1 amp per meter, which is equivalent to 100 amp per square centimeter, given our contact length. So the program will try to use the maximum step to sweep the voltage from 0 to the target voltage, leading to 1 amp per meter. When the convergence cannot be reached, a smaller step will be used. If the step is smaller than the minimum step, then the program will be terminated automatically with an error message: convergence cannot be reached. You can check the similar simulation results in these two links. They are uploaded on 443 course website. There's a report and a slides. But I think the important knowledge that you should learn from this presentation is that you know how to modify your macro file, and you know how to include your customized materials in a dot layer file. You know how to read in how to use the macro file in the solution file. I think that is for today. Thank you very much for watching this. Hope you learned something. Thank you.